In this problem, we have two rollers, A and B. They are connected by a rod AB. They're pinned together to the rod. And the roller A rolls to the right, and we assume that it rolls without slipping, and its center point A has a constant velocity of 0.2 meter per second. So we need to determine the linear velocity of point B as well as the angular velocity of rod AB, both as functions of angle theta. So we're again going to use the absolute motion analysis. So the first thing we want to do is to choose a fixed datum. So this is the datum for theta. For convenience, theta is defined as this angle right here, clockwise. So clockwise in this problem is considered positive. And let's choose another datum. The reason is because we need a position vector for point A as well as a position vector for point B. So this is a fixed point. Therefore, this right here is SA, the position vector of point A starting from a fixed point. And this right here is the position vector SB, again starting from a fixed point. So as you can clearly tell, according to trigonometry, SA equals to rod AB, which has the constant length of 0.6 meter times cosine theta. So let's work on this first. Well, actually, let's do this first. SB equals to simply 0.6 times sine theta. So if we take this equation and then we take the time derivative of both sides. So on the left-hand side, we have dSA dt. On the right-hand side, we have 0.6 times d cosine theta dt. Using chain rule, that equals to 0.6 d cosine theta d theta times d theta dt. So the left-hand side, dSA dt, it does equal to VA, which equals to 0.2 meter per second that's given. And then on the right-hand side, we have 0.6 d cosine theta d theta, that is negative sine theta, and then d theta dt is omega AB. So from here, we can solve for omega AB as a function of theta, and that equals to 0.2 divided by negative 0.6 sine theta, which equals to negative 1/3 1 over sine theta. So if you want to, this equals to negative 0.333 cosecant theta. So that's part of this problem solved. Omega AB, the angular velocity of rod AB, expressed as a function of theta. And then we move on to find SB. From here, SB equals to 0.6 times sine theta, taking the time derivative of both ends again. So we will have dSB dt. No need to use red, use blue. dSB dt equals to 0.6 times d sine theta dt. And following the same procedure, using the chain rule again, d theta dt. So left-hand side is VB. It's defined this way, up to be positive. Look at the direction of SB. This equals to 0.6 cosine theta times d theta dt, which is omega AB. Don't forget omega AB, we have determined from earlier, equals to negative 0.333 cosecant theta, which is 1 over sine theta. Therefore, as a result, VB equals to negative 0.2 cotangent theta. And that solved the first part of this problem, VB expressed as a function of theta.